Hi everyone, my name is Thejas and today me and my partner Anujith is going to discuss a few things about dimensionality reduction using principal component analysis. Principal component analysis is a dimensional reduction method used to transform a large set of variables into a smaller set of variables while still retaining most of the information of the larger set. We are trying to reduce it into a smaller variable set because it will be easier to explore and visualize and also analyze the data, and the machine learning algorithms can also be better implemented on a smaller data set. It's not better, it's more, it can be implemented faster. So the reducing comes at a cost of accuracy. So essentially we are trying to optimize this trade-off to get highest simplicity for the little accuracy deficiency. PCA consists of 5 steps. First one is the range of continuous initial variables are standardized. Then the covariance matrix is calculated to identify the correlations. The third step is to compute the eigenvalues and eigenvectors. Of the covariant matrix, so that we can identify the principal components. The fourth step is to create a feature vector which will contain the necessary principal components. And we will remove the rest depending if there is a high eigenvalue or not. And the fifth one is to recast the data along principal component axis. First I will check into the first step, standardization. So why are we doing this? So what we do is we standardize the range of initial variables using a mathematical formula. So why are we doing this? This is because it is critical to perform standardization because that PCA is quite sensitive regarding the variances of the initial variables. So if there is a large difference between initial variables, that will dominate over the small ranges. For example, if there is a variable with ranging over 1 to 100 and another one ranging over 0 to 1, maybe 0 to 100 and 0 to 1, this will have a higher bias towards the analysis. So we will try to scale it into a standardized unit. So what we do is we calculated z value by the following formula. Then after the standardization, all the variables will be transformed into the same scale. Then the next step is covariance matrix calculation. So the aim of this step is to understand any relationship between the variables. So how the variables of the input data are varying from the mean respect to each other. Because sometimes variables are highly correlated in such a way that they contain redundant information. So in order to identify these correlations, we compute the covariance matrix. So a covariance matrix is a p by 2 symmetric matrix which has its entries the covariance associated with all possible pairs of initial variables. So for example, for a three-dimensional data set with let's say three variable x, y and z, the covariance matrix will be a 3 by 3 matrix such that each element will be looking between the covariance of variable and itself in the diagonals and all other possible combinations in other places. For the diagonal terms, covariance of that to itself will be basically the variance of that element. And since the covariance is commutative, or AB covariance will be equal to that of PA, so that the matrix will be symmetric with respect to the diagonal. So the upper and lower triangle portions will be equal. So the reason for doing this is that if it's positive, then two variables increase or decrease together. If it's negative, then one increases and the other one decreases. So it's we can identify if the variables are correlated or inversely correlated. Then the next step is the computation of eigenvalues and eigenvectors. So that we can identify the principal components. Eigenvectors and eigenvalues are the linear algebra concepts that we need to compute from the covariance matrix in order to determine the principal components of the data. So the principal components are new variables that are constructed as linear combination or the mixtures of initial variables. These combinations are done in such a way that new variables are uncorrelated and most of the information within the initial variables is compressed into first components. New variables are uncorrelated and most information are within the first or initial variables of the initial variables compressed into the first components. So for example, a 10-dimensional data will give about 10 principal components, so that the PCA tries to put maximum possible information in the first component, then the maximum remaining information into the second component, and so on. Organizing information in principal components this way will allow you to reduce dimensionality without losing much information, and by discarding the components with low information, considering the remaining components as your new variables. By discarding low info variables, dimensionality can be efficiently reduced without much loss of information. Geometrically, principal components represent the direction of the data that explain the maximal amount of variance. So, larger the variance, more information that line will have. The more the dispersed across a variable, more information that variable will have. So we can visualize the importance of specific variables. So principal components as new axis would provide the best angle to see and evaluate the data, so that the differences between the observations are better visible. As there are many principal components as there are variables, principal components are constructed in such a manner that the first principal component accounts for the largest possible variance in the dataset. Then the second principal component will have the second highest variance and is also uncorrelated with the first principal component, and so on. This continues until a total of P principal components have been calculated, which is equal to the original number of variables. Since the eigenvectors comes in always in pairs, every eigenvectors will have an eigenvalue and the number is equal to the number of dimensions of the data. So the eigenvectors of the covariance matrix are actually the directions of the axis where there is the most variance, or most variance means most information also, and these are the principal components. So these eigenvalues, which are the coefficient of the eigenvectors, would represent the amount of variance carried in each principal components. Now the next step will be making of feature vector. In this step, what we do is to choose whether to keep all the components or discard those of the lesser significance, that is the components with low eigenvalues, and form with the remaining ones a matrix of vectors that we will call feature vectors. Depending on the eigenvalue. Low eigenvalue means that component is not that important. High eigenvalue or variance means we have to keep that to get a better result. The feature vector is simply a matrix that has columns of eigenvectors, and this will be the first step towards dimensionality reduction, because we only keep let's say p eigenvectors out of n, so the final data set will have a p dimension which is less than n. So we just want to describe our data in terms of new variables that are uncorrelated without seeking to reduce dimensionality, leaving out the lesser significant components. So this will be the first major step towards the dimensionality reduction. And the last step would be recasting the data along the principal components axis. In this step, the aim is to use a feature vector formed using the eigenvectors of the covariance matrix to reorient the data from the original axis to the ones represented by the principal components. So that's why it's called the principal component analysis, and this can be done by multiplying the transforms of the original dataset by the transfer of the feature vector. So the final dataset equals feature vector transpose multiplied by standardized original dataset. For the next part, my teammate Anujith would elaborate a numerical example and try to find the principal components.
The principal component analysis or the PCA can be best explained by using a numerical example. Consider the matrix X. Here X gives the measurement of water. The first column is the thickness, the second column is the horizontal displacement, and the third column is the vertical displacement of the water, where X is a 3 measurement matrix. Now we need to compute the correlation matrix. We can compute the correlation matrix by computing the correlation between the thickness and the horizontal displacement, the thickness and the vertical displacement, the horizontal displacement and the vertical displacement. So the correlation matrix R would be this matrix. In this, the diagonal element is 1. This is because here it shows the correlation between the first column and the first column, which would always be 1. That is, it shows the correlation between thickness and thickness, which would always be 1. Similarly, this shows the correlation between the horizontal displacement and the horizontal displacement, which would always be 1. And the case is similar for the third case also. You can also see that the upper triangle and the lower triangle are having the same values. This is because it shows the correlation between the same elements or the same column, as they are having the same test. The next step is to find the eigenvalue which satisfies R minus lambda I equal to 0, where I is the identity matrix and R is the same matrix. Let A equal to R minus lambda I. We are using this to make our calculation much easier. So determinant of A equal to determinant of R minus lambda I, which would be equal to this matrix. Now we are going to substitute X equal to 1 minus lambda in order to make our calculation easier. So 0 equal to determinant of A, which would be equal to this would be equal to x cube minus 0.543 x plus 0.03886. Now we need to find the root of this equation. It has 3 roots, which are x equal to minus 0.769, 0.073 and 0.696. But we already know that x is equal to 1 minus lambda. So lambda would be equal to 1 minus x. So lambda 1 is equal to 1.769, lambda 2 equal to 0.927 and lambda 3 equal to 0.304. These are the 3 eigenvalues. It can be seen that the sum of lambda 1, lambda 2 and lambda 3 is equal to 3, which is the same as the trace of R, that is the sum of the main diagonal element. Similarly, we can also see that the product of lambda 1, lambda 2, lambda 3 is equal to 0.499, which is same as determinant of R. Next, we need to find the value of V. For finding the value of V, we need to find the value of each column. We can find this by substituting lambda equal to lambda 1 in A and multiplying A with the first column of V, that is, now by solving for the equation we would be getting V1 equal to 0.064, V21 equal to 0.69 and V31 equal to 0.34 negative. Now similarly we are going to substitute lambda equal to lambda 2 and lambda 3 in the matrix A and find the remaining values of the matrix V. After that calculation, the matrix V that we would be getting would be, the V is having an additional property, that is, if we multiply V by its transpose matrix V dash, then we would be getting the identity matrix I. Now we need to find L1 by 2, where L1 by 2 is the root of the eigenvalues of R. That is L1 by 2 is the root of the mode of each eigenvalue lambda 1, lambda 2 and lambda 3. Now we need to find the factor structure S. The S is equal to V into L1 by 2. That is, we need to multiply this matrix with this matrix in order to get S. So the value of S would be, here S shows the correlation between the variables and the principal component. For example, consider 0.91. This shows the correlation between the second variable and the first principal component. The next step is to compute the communality between the first two eigenvalues. That is, we are just considering these two eigenvalues. So S into S transpose would be equal to, we are getting this value by multiplying this matrix with its transpose. The communality consists of the diagonal elements of this matrix. That is, the first two principal components explains 86.62% for the first variable, 84.2% for the second variable and 98.76% for the third variables. That is, the first principal components are explaining these steps from the diagonal of this matrix. In the next step, we are finding the coefficient matrix B is formed by using the diagonals of the reciprocal of L1 by 2 matrix, that is B, which is equal to V into L minus 1 by 2, where L minus 1 by 2 is the reciprocal of the diagonal of this matrix. So in this step we are multiplying the matrix V with the reciprocal of the diagonal of this matrix. So the value of B would be now the next step is to create a matrix set which is the standard score form of the matrix X that we wrote in the beginning of the example. Now we are going to compute F, which is equal to set into B. We have explained both the matrix above. The columns of this matrix are principal factors. This would be the matrix F, which is equal to set B. The factors plotted against the indices would be times. If the time is used, then the resulting plot is an example of the principal factor control chart.